All right. Hi, everyone. We're going to get started around Berkeley time. Uh, we are recording. We will get the recording out there. We'll figure out how to get it out to people at the end of the meeting, but we will get it to you sometime. Um, but yeah, I'm also in 106, so I'm here to be learning, but my Teely and I are the co-presidents of Pi Tau Sigma. So my Teely and Anant will be running the review. We'll be going over some homework solutions and practice problems, especially since the professor was emphasizing homework 7 and 8 for the exam. And then we'll have some time at the end for questions and problems, if we have extra time problems that people suggest. But yeah, we'll be starting at Berkeley time. All right, so it's about Berkeley time. Again, just want to introduce ourselves. My name is James. I'm also in ME106, so I will not be helping the lead. I'll be learning as well, but I'm one of the Pi Tau Sigma co-presidents with Mike Teely, and then Anant is another one of our officers, and they both will be helping to lead this review, and we'll be going over problems and the homework 7 and 8 solutions. And then at the sometime at the end, we'll give you guys time to ask questions slash suggest some problems. But yeah, we can get going. It's recording. We should be posting it on our website. We have a Pi Tau Sigma website, but I will also ask the professor to send out a copy of the recording. All right, my Teely and Anant, that is all you guys.
All right, so yeah, I'll be going first. I'll go over I'll be going over homework 7 and 8, like select problems from those. And then Mike Lee will be going over the some of the old textbook, the old Tau Beta Pi questions. So let me share. Okay. So I'll go over the professor's problem from homework 7 first before going over the Munson stuff. And then for homework 8, for specifically since problem 2 has a lot of different notation going on, I won't like go over that like line by line. So if there's any specific questions on that one, we can go over it at the end. And then yeah, we can go over that together. So okay. And if you guys want to keep the like solutions or like just the homework problems on hand so you can follow along, that would probably help. But yeah, the first question. So the first question is a little bit of a complicated like conservation of mass, conservation of momentum question. So for part A, most of the stuff is pretty simple. Or by finding most of the variables is not too bad. It's just when you get to the force in X and force in Z, it gets a little bit weird. But then, oh, and also, James, if anyone has questions in the chat, you can just like field them to me at some point. Yeah.
Yeah, that sounds good.
Okay. Okay. So the first thing we're supposed to find is um, V3. So how do we do this? So in terms of this problem, they want us to make that control volume that looks like this is the thing they have. A little pipe coming out here. They have water coming out the bottom here. Okay, so the first part, finding V3 is pretty simple. So in terms of CV1, you have an inlet over here, an outlet over here. And then if you just apply basic conservation of mass, you get, and the density is constant. So rho A3 V3 is equal to rho A1 B1. And then from that, you can simply rearrange stuff to get V3 is equal to V1 times A1 over A3. So this is simple because there's in this control volume, there's just one inlet and one outlet, and the surfaces of the control volume are normal to the mass flow, so you don't have to deal with any angle changes yet. So that's the first one. And then for the second one, to find H, we would be using the Bernoulli's for this one. So this is V, let's go H. So for Bernoulli's, we have half rho V3 squared is equal to half rho V4 squared plus rho GH. And then I'll also write what 4, 3, 2, 1. So we know that what V4 is 0, it's station the because H is stationary, so that entire term goes away. We know what we're trying to find H, and then we from the first equation, we know what V3 is. So then simply again, just rearranging stuff, you get that H is equal to V3 squared over 2G. And then you can substitute V3 from the first term that you found. And then the next one is V2. So V2 is also a form of Bernoulli's. So now instead of this streamline, this was for H, we have to use the streamline from the pipe to the top of the water. Again, if my drawing is a little bit bad, you can also just keep the solutions open on the side. So for V2, there's another form of Bernoulli's. So you're starting at the pipe entrance, so you have half rho V1 squared plus rho G capital H is equal to half rho V2 squared plus rho G, the smaller h, because that's the height difference. And then again, you can just rearrange everything and then you end up with V2. So it's pretty basic thus far. You're just either using conservation of mass or using Bernoulli's. So then the next term we need to find is H. Oh, no, not H, sorry. Oh, we need to find V2, we need to find theta 2, sorry. Okay, so they go over it a little extra steps, but just through intuition, the way you can find theta 2 is that so if you just know like a basic physics problem, you can see, okay, the water is leaving the spout and it's going down into the water. The only force that's acting on it is gravity. So there's only a force in the y direction and there's no force in the x direction. And if you, from like high school physics, if you remember projectile motion, you know that the velocity in the x direction remains constant. And that's something that comes into play here as well. So you can just use the fact that v1x is equal to v2x, and then v1x is also equal to v1 cosine theta 1. And you also know that v2x is equal to v2 cosine theta 2. Or v2x is equal to v2 cosine theta 2. And if you just combine those two, you can find that. So let's combine them. We'll go with v1 cosine theta 1 is equal to v2 cosine theta 2. And then you get cos theta 2. Cosine theta 2 is equal to v1 cosine theta 1 over v2. Okay, so that's how you find theta 2. And then you need to find A2. A2 is also pretty simple. There is one step you have to take for this thing. So what you could say, or the way that they did it a little bit I'm doing it slightly backwards, but the way that I imagine this happening was you can say, again, we look at our control volume. You have an outlet here. Okay, so this one requires the second control volume. So let's see, and it goes like this, right? And then it goes into the water. So then I just make that in red. This is our control volume here. And notice in this case as well, the control volume is it's and the flow is normal in both these directions. So that just gets rid of one set of signs, one set of angles that you have to deal with. So for A2, the way that I'm doing it is that, okay, I know that there's flow coming in through here, there's conservation of mass, and I'll neglect rho for now because we know that the density is constant, that just cancels out. So we have A1 V1 is equal to the flow coming out of this part. And that becomes, so in the solutions, they define this as A2 prime because the A2 that they define here is what's normal to the flow, something like that. That's the actual A2. So so for now you don't need that. You can just say that A2 is equal to A1 V1 is equal to A2 prime, A2 prime, and then the velocity in the velocity that's normal to the uh, A2 prime direction. So what that is V2 sine theta. And that just comes from V dot N. And that comes in some other equations, but if you just do that, you get A2 V2 sine theta. And then if you did a little bit of geometry on this part, you get the relation that A2 is equal to A2 prime sine theta. And then you can just rearrange terms. So then this A2 sine theta comes in over here. And then you get A1 V1 is equal to A2 V2. And then it just becomes simply A2 is equal to A1 V1 over V2. Okay, that's um those are the easy ones. Just any questions so far on any of that? Feel free to just put them in the chat if there's anything. Okay. So then for the next part, we need to find the um the force in the x direction. So what we know that okay, yeah. So let's go over what A2 prime is again. So maybe I can draw it a little better, but so we basically have the pipe. The pipe is like a straight pipe here, and then the water comes out and it curves a little bit because of gravity, and it hits the free surface of the tank of water at theta 2, and this is theta 1. Let's just make that clear. Okay, so this area, this area down here, just like simply like how much ever is hitting the tank, this is being classified as A2 prime. So the actual A2, the one that they're asking you to find, is like this projected area here, because at this, or how I should, oh, why is my eraser not working? But at this specific point, the velocity is coming in this direction. That is not, it's not perpendicular to the flow over here. So there is some angle that this velocity is coming at, and that angle, and it's the same, it'll be like sine theta, it'll be like a sine theta too. So this part here, the part that's, oh, where did that go? Yeah. So this part here is A2 prime. But when you want whatever is perpendicular to the flow velocity, that's what you're asked to solve for, that's A2. And then again, if you did a little bit of geometry over there, you'd figure out that A2, the relation between A2 and A2 prime is just A2 is equal to A2 prime times sine theta. So I think that's given if you go to the solution as well, it'll say in the bottom of like the big paragraph for the question, the cross-sectional areas perpendicular to the flow velocities are A1, A2, A3. So the A2 prime is not perpendicular to the flow velocity, but it's horizontal with respect to the tank. But A2 is the one that's perpendicular. Okay. So then, oh yeah, so now let's find fx and fz. So then, let's just put it here. So then for this one, you need to use the conservation of momentum. So I'm gonna label it just capital M in this for this notation is equal to 0 because it's all steady state. It's all steady and nothing, and the tank and everything is not moving. So there has to be 0 net momentum change. So then, and this is equal to f of x plus rho a1 n1 dot v1 times the x direction times v1 plus rho a3. Oh, okay, and then for this one, we'll be using the, let me draw this out as well. I'm gonna erase this part of it. So for this one, we'll be using the control volume, which is just the tank. Yeah. So for this one, we would be using, or no, for this one, we use the full control volume, sorry. So this one, we go back to our top one over here. We have the full control volume with this. We have the pipe coming in, and we have the water coming out. So this is the one we're using for this one. So here we have, okay, so we have N3 dot V3 and then X dot V3. Okay, so again here, so, and then we need to find this f of x force, whatever that is. So we have this top part here. So then the way that this works is that it's split up into your force and it's split up into your momentum flux. And then the key thing to remember, or when you're trying to remember what like the momentum flux equation is, that there's obviously there's um, the density and the area, this part, but where the actual velocity comes into play, and when you get all these different like thetas that you need to think about, the easiest way to think about it is that there's two pieces of information that you're being given. You're being given, or that you need to like put in your equation. The first one is it a inflow? Basically, is it an inflow or an outflow? And then so this term will usually not have the um, your like angles to it because this will just tell you if it's coming in or coming out. And in Professor Marcus's case, he says this is the normal and it's going inside of the volume. So that tells you if it's an inflow or outflow of momentum. And then this part will tell you the direction of it. So if we were to write this out, or let's see what each of these terms are. So N1, V1, this is um, um, this is at the normal force is in the same direction as your velocity, so there's no angles that come into here, so you'll just, and this will just be v1, and since it's a positive term, that means it's coming inside of it's an inflow of mass of momentum. And then here for n3 dot v3, so this is so v3 is going in the negative, oh, isn't going the negative z direction, and then n is going into the positive z direction, so this will just be v3. And so this will be negative because it's in opposite directions. And then if you go to this term, the x dot v3 term, v3 is only in the z direction, so this is 0, which cancels out this entire term. And then the last term, we have this x dot v1. So that basically just tells you how much of the velocity is in the x direction because we're looking at momentum in the x direction. So this term, so we just write here x dot v1 is equal to v1 or negative v1 cos theta 1. So then you can plug that into here, and then you'll finally get that f of x is equal to rho a1. Another question, sorry. Okay. Rho a1 v1 squared cosine theta 1. Cool. So again, the big part to remember is it an inflow or an outflow here? And then is it in what is the direction of the velocity with respect to the direction of your momentum flux that you're calculating? So okay, so that'll give you the solution for the force in the x direction, and now force in the z direction. So same thing, we have momentum in the z is equal to 0 because nothing's moving. So then you have, or it's the rate, right? Yeah, that's fine. So then you have force in the z direction, and then this time in the z direction there's gravity, and then oh, and so the control volume for this one is, I should probably write that down. The control volume for this one is just the tank because we don't know the weight of the water coming into the stream yet, so we don't want to include that as part of our control volume. So it's just this. There's a theta 2 momentum coming in, and there is your uh, momentum going, or your mass flow going out here, which will cause the momentum change. So this is your CV in this case, just the tank, just the tank. Okay. So then if we do for FX, why were you able to switch signs? Shouldn't it be negative? Um, no, because we're moving. So okay, maybe I should have written that down a little bit clearer, but okay, let's get that out of the way. So we have the same thing. We have so once we okay, let's simplify this one time. You have 0 is equal to f of x plus rho a1 v1 negative v1 cosine theta 1. Sorry, guys. Okay, so then there's a negative sign here. So then so this is a positive and a negative. So you just move it over and then you'll get the same thing. It's equal to rho a1 v1 squared cosine theta 1. So remember, this term is negative because the flow is in the opposite direction of the x of your defined positive x direction. Okay, so then for the z momentum, then you have to subtract rho g h a because I mean, so this is just same thing as mg. This is your volume. This is volume density times gravity. So that just comes out to just basically mg, and that's in the negative direction because gravity always points downwards. And then you have the same stuff that we had before. So we have rho a2, and this time there's a2 prime because we're looking at this. We're looking at the area that's in the same like the. So we're making sure the control volume is in the same as like not creating an angle with the area that's coming in. So that's why we're using the A2 prime in this case. And then we have the same thing. We have and then A2 prime is in the negative z direction. So you have negative z. I'll just write as a normal for now. N dot, yeah, the exact same stuff. So then we have, and then z direction. So z dot v2 plus the rho a3 and 3 dot v3 z dot v3. Okay, so yeah. So then in this case again, let's go over each of these terms. So this is is it an inflow or an outflow? And in this case it's an inflow. So we have this is just going to be v2, and in this case this is an outflow. So this is going to be a negative. This is going to be a negative v3 term. And then you have, again, z dot v2 is just negative v2 because v2 is coming directly in the negative z direction. And then n3 dot v3, again, this will be a this will be a negative v3 because the n3 is pointing the capital z direction. So then at the end, with all of this stuff, you will get that. Oh. Oh, are you guys be able to see my screen? I feel like something just happened. You guys can't see me. Here, let me see if I can reshare this. They gave me an error on my end.
think we're still able to see it. But yeah, you try sharing again.
Oh, interesting. Yeah, I don't know what happened there. Okay. Let me reshare the content. Okay. Okay. Working on zooming. Okay, now let's go here. All right, so sorry, back here. So then same thing, if we go through the same, just like moving stuff around, we'll get that F2 is equal to rho GHA plus rho A2 V2 squared. Oh, wait, I not. Oh, sorry, that's my bad. So in this case, that's my fault. So we have so this V2, remember, so even though this A2 is in the normal direction, this V2 is actually coming in at this angle theta 2. So then this, so we have this N dot V2 is actually going to be V2 sine theta 2. Yeah, sorry about that. And then Z dot V2 is equal to negative V2 sine theta 2. Okay. So then you have these terms. So then sine theta 2 minus rho A3 V3 squared. Okay, so this stuff makes sense. Over here, there's a small simplification I made where, notice how there's A2 here. So I basically used, so this would have been rho A2 prime V2 squared sine squared theta 2, but you can combine A2 prime with one of the sine thetas, and then it'll just simplify to this. So does this make sense? So this is, again, this is a positive, this on a sine basis is a positive value because, oh, so we chose the tank as the CV because we don't know the weight of the water. So like in the next part, you have to find the weight of the water, or in part B, you have to find the weight that comes from the actual flow of the water coming into the pipe. So in this at this stage, you don't know what that weight is, so you can't use the entirety of you can't use the large control volume for this thing because that also encapsulates the flow coming out of the pipe. So you would have an extra term here in that case regarding the weight of the thing. And you'll see, and if you go into so I'll go over this right now basically, but so that's not a pressure contribution, rho G, that's the weight of the actual water in the tank. So it's just, so again, rho GH is just H times A is the volume, rho is the density, so volume times density is mass, times gravity is just mg. So it's just the weight of the water in the tank. And there's no pressure contribution because the boat 4 is assumed to be at surface level, so atmospheric pressure, and 3 is assumed to be like a free flowing nozzles that's also at atmospheric pressure. And it says in the thing, all control volume boundaries have PATM, atmospheric pressure. So yeah, let's do that. Okay, so if we go to part B, okay, part B, we have now find the mass of the water. Okay, so this is what we were talking about when we were going through we were finding we were talking about the weight of the actual water in the jet. So in this case, so this is large CV. So the one that looks like, I'm gonna say it right like this. The one that looks like this with the actual pipe coming into it. So in this case, we have, again, the same. So we're going to use the exact same momentum equation. And then we have, oh, this should be Z. Sorry. This is equal to, we have FZ minus rho GHA like we did, but this time we have the weight of the jet. Yeah, we have the weight of the jet, and then we have plus, and then we have the same, we have almost the same contributions that we had before. We have a plus rho A1, N1 dot V1, Z dot V1, plus rho A3, N3 dot V3, Z dot V3. Okay, so again, if you go through all these things, you can find what the angles will be. But basically, at the end of this thing, so I'll go over like the only thing that's different, which is this term over here, this term over here. So then this N1 V1 is an inflow, and this is perpendicular. This is in the same direction as the normal vectors. This is the same direction as the velocity. So this is just V1, and then over here you'll get a negative V1 sine theta because it's in the opposite direction of Z and it's the Y component basically, or the Z component basically. So those are your two new terms. And then again, if you rearrange everything, you'll get W jet is equal to F2 minus rho GHA minus rho A1 D1 squared sine theta plus rho A3 V3 squared. Okay. And then and then from the mass, you can just do the weight of the jet divided by G is equal to mass mg. All right. And that's given in the solutions as well. So that's the basic way to do this. The other problems from the Munson book have the same kind of they have a similar stuff to it. Honestly, I feel like this problem was probably the more complicated one because of the two different streamlines you're supposed to use and the three different control volumes. So so the rest of them should be there. They should be fine. I was looking at the solutions and there was a slight sign error with some of the um for a problem 5.35, like literally the first Munson problem that they give in some of the when they're finding like the momentum change in the x and the y direction, x in the x in the y direction, but the end equation is still the same. So just like if you're looking at the solutions, I guess watch out for that because I saw that. Okay, so I took a good amount of time on this one, but let's go to the professor stuff for homework 8. So just by a show of hands, which problem is probably the one that you guys would like to see the most? Because there's the firefighter problem, there's um the cart one. Okay, is everyone wants to hear about the cart one? Okay, cool. So again, as I said, I won't go through the cart one line by line because it is a lot of notation. But if there are like specific questions, we can just go over the solutions together and figure it out. So let me actually stop sharing um on my iPad and then we can okay, actually it just broke. So that's great timing. Okay, I'm just gonna leave on my iPad. Okay, cool. Let me see. Okay, let me now just share on my screen here. I just have the solutions open up here. Okay, let's just share what I want to share. Slack. Okay, here it is. Okay, and then is yeah, you can either ask a question or you can just like raise your hand or something. I feel like that might be a little better. Okay, we're just sharing this, right? Okay. Let's go to the homework 8.
So I'm not. Daniel just left a question saying, he said that what was confusing was deciding what frame to use, and also converting between the different frames, especially the velocities, depending on what part or
Mhm.
where we're solving.
Okay, so I guess the main thing in this question is that um there are, I mean, there's three frames, right? There's the inertial frame, which is just like you're stationary watching this cart move. Then um, you also have like the accelerating frame, which just moves with the cart. Those two make the most sense. The one about the one where it's like the frame is moving at a constant velocity, it's not even per this thing, it's not like used too much other than to like change the notation a little bit. So I guess as a rule of thumb, so you sort of find the one that makes it easiest for you to solve it. So in this case, for like parts A and B, they're using the accelerating frame, right? So the reason why you'd use the accelerating frame for part A, let's say, is because, well, you know the velocity of the water coming out in the accelerating frame already. So otherwise, you can use any frame you want, and they also give you the relations to like do that. Oh, not here, but in the problem statement, they give you the relations to like convert for especially for like this water velocity. They give you like the stuff to convert between it, but at least for this one, it's like clear that like okay, like if I want to use a singular term for my expression, it's gonna have to be with the inertial frame. So it's mainly about thinking which one gives you which one just makes your calculations simpler. And even for the second one. So in this case, they kind of jump between two frames, right? So they first have their initial equation in the same way as part A in just the uh, frame, the accelerating frame, but then afterwards but you don't know this what this copper velocity is. So then you have to convert your frame into the inertial frame, and then in your inertial frame, you know that the copper doesn't move, so that's going to be 0. And then you can use that, and it tells you can use the cart velocity. So that's another hint, I guess. And but then you can use since this velocity is unknown, so you started with the simplest equation in the accelerating frame, but then you found one unknown in this frame, so you had to convert to the inertial frame to figure out those values. So it's basically, I guess, start off with the frame that's the simplest to have the equation in. And then when you find terms that you're not able to like you don't have as a given, you haven't solved for already in that frame, then you have to convert to like in this case just the inertial frame. Yeah, let me see. Let me just keep chat open here. Um, yeah, so I mean, in this case, it's more like you just so yeah, they tell you what the velocities look like. So it's that same equation where like v tilde is equal to v prime minus v prime cart. So just since since that was given to you, that is like the equation to use to convert between frames. Yeah. Any others question that people have on this? No, okay. If you guys want, I can just like kind of go over it just briefly with the solution. So obviously in this one, you use the. Are there any other questions, James, or no? Okay,
No,
cool. So I'm assuming people are still confused about this. So I'll just go through it line by line in the solution key because I think it's a lot to like write down. So the first thing, obviously, so you find the rate of the water leaving the cart. So the inertial frame gives you the simplest equation, and you know this water leaving velocity. So you just put the rate as the water leaving the cart is equal to just a rho AV, which is just the mass conservation equation. And then you just integrate that over time, and then you have an initial condition where you know the mass of the water at time equals 0, and then it's just multiplying by t because it's a constant that you're integrating. And then the second part A similar thing, you have a mass rate equation. What you have to find are the key parts to know that the copper is not moving. So then that allow you to convert this velocity in the accelerating frame of the copper as the negative of the cart velocity. And then from there, you do the same integration. Over here, it's not you have to, since the cart velocity depends on time, it's not a constant. So when you do this integration, you can pull out the A in the row over here, but this thing has to be integrated over time. So that's just what this means. Just integrate the velocity of the cart over time the um to put it into the expression for the mass of copper. Okay. And then the next part, now here you're finding the different like components of momentum. So over here, so you're basically doing the same thing where you're getting mass times velocity as your momentum. And then they've put it into this frame, but I think that's okay. They put it into this frame because you're given a relationship between um like this part of it over here is given as part of like the problem statement. So it's just different ways to simplify what's happening. So so in this case, you just take a product rule derivative. You just take the derivative of this expression and it is just the product rule. There is a special like thing with this like this integrand is dependent on time. So there is like a, s- a specific formula that when you take the derivative, it comes out to like this piece. But then the second part is basically the same thing. So you just take this entire part take the derivative with respect to time, and then it'll just come out it comes out to that you're um like you just get to a part of the equation where you can plug in uh a car velocity from your givens, and that's how this one works. It's a little yeah, even when I was going through this problem, it was a little like annoying to do. But I think it's more about just figuring out the best way to simplify the equation. So what else is here? Again, okay. So- Okay, then yeah, and then the other ones are a lot simpler. It's not as like weird as this one is. It's just basically you just for this one you just take again time derivative. You know the momentum of the water is just the mass of water times the velocity of the cart. So then you just take the derivative and you know what all these different terms are from your A and B. So then you figure it out. So I think it's just getting this momentum and the time derivative of this one, which is the weird one, because everything else is pretty straightforward. You're just using what you have in the previous examples. Um,
No, there's another question about the integral for C4 and D4 and how we arrived at that.
for this one,
Yeah.
okay. Um, so I think so for this one, it's the same thing because so you have the V of I think the main thing to learn from this one is that since the copper doesn't move in the inertial frame, you can just set the momentum of the copper to zero. The way they come to the actual the way they come to the integral of this part is the same. Oh, so this part is just okay, let me see if I can open the actual card problem. Okay, where's the so that part of the integral is just this last section. So this thing is already, so you have the momentum, like the mass of this thing is changing, and then the card is moving. So you already have the contribution of to the momentum from this thing. But then this specific part over here is what they're looking for, which is it is technically trivial just because again, in the inertial frame, this isn't moving at all. So you're just the same way how you took the for the water momentum here, you took it from the start all the way up until this point, and that'll give you like mass. That'll give you the velocity times the mass because you take rho times like the volume that it's occupied. Rho times that volume is equal to the mass. So in the same way that you had to take that integral over here, you have to take the same integral from B to L. And it's the same thing. You have it's the same thing. I'll try to keep this as brief as I can. But you have the exact same thing. So you take your integral from B to the end, and then you have your rho copper, A copper, which can be pulled out anyway, and then using to integrate this velocity over time. And so you can see it's of the same form as what's happening over here. But the main thing to remember, I think, in this case is, I guess the integral is part of it, but like in this case, there's probably a really big simplification you can make, which is that this V copper is just zero. So yeah. Okay, it's getting pretty close to the end. We could, if you guys are still like down to stay, we could go over the other practice problem. That's like a syringe. I don't know if you guys have already looked at it yet, but it's like the syringe moving. It's similar to concepts from homework 7,
There
or
was
we could just
another.
go over some general questions.
Sorry to interrupt. There was another question about
Oh yeah.
going. I believe this is going back to the general control volume analysis for like the rate of momentum, but someone was
Hmm.
asking about the difference between the like accounting direction versus like the normal direction. Um,
The what
like
direction versus the
for lectures, we've described it as the accounting direction, but basically how there was like the normal vector times the velocity times the vector that the like vector that the axis that we're taking the momentum rate is in
yeah.
times the velocity. There was someone was asking for clarification about that, like for problem
Okay, so
homework
yeah.
7, problem 1.
Okay, yeah. So in the same way that I had like yeah, like in the same way that I had written it, let's see if I can just keep that open as well, since I've already unshared my iPad. But okay, over here, basically. So then you have these two things. So the way that I think of it is that this first part, the normal one, describes the inflow you have into your control volume. So this just tells you what is it coming in, is it coming out? And then that it'll switch signs depending on that. That's why over here you see that in this equation, you add all the terms. You're not like implicitly like making something negative because you know it's like coming out of like the control volume or anything. You just keep it simple, keep everything positive. And then this term itself will tell you, okay, should I swap the sign? Should I make it a negative or not? So this term, the normal term, a normal term will usually just give you like a sign difference. It didn't as you can see in the very end, it didn't. We had like this term actually gave us, where was it? Oh, over here, yeah. This term actually did not give us, this V2 was not in the same direction as the thing, but in most cases, you like orient your, where'd it go? Oh, here it is. You orient your normal such that it's um the normal such that it's in the same plane as the control volume. So this just tells you, is it coming in? Is it coming out? Usually there's not an angle associated with it, but as you saw, sometimes it does. And then this one tells you like, okay, how much of that velocity, because we don't care about the velocity in the y direction because we're looking at momentum in the x right now. So it just tells you which part of the velocity I need to care about. So it's just taking the x component or like whatever axis component in of the velocity you want. So this thing dictates inflow outflow. This thing dictates the direction basically of your um the direction of your velocity, or like which component you're interested in.
Okay, it is already 6 o'clock, so maybe if we have any final quick questions. If not, then we can end it for the day.
Yeah, and I guess like since we weren't able to like like cover like in this thing the tau beta pi 2005 question, just make sure you just go over that on your own time, because that'll if you haven't already seen that, because that'll probably give you a little bit more practice into this type of question.
All right. If we do not have any more questions, then that'll be the end of it. Again, I just posted the website link in the chat for Pi Tau Sigma, and we'll be posting it on there hopefully by the end of tonight. And we'll also ask the professor to send out the recording. But thank you so much for joining. Good luck to everyone on Friday. I know I will definitely be needing it, but everyone's going to do great.
Yep, thanks
All
everyone.
right. Thank you.